Good day, friends. Welcome back to Smart Booklet. In today's video, we are going to be solving another problem in relation to Gauss law. Firstly, let's get the overview of Gauss law. Gauss law states that Gauss law it states that the total electric flux out of any closed surface. So let's have a closed surface. The total electric, if there's electric field coming out, right? So the flow of that electric field is called the flux. So the total electric flux out of any closed surface is equal to what? The electric charge inside, right? The surface, the Gaussian surface divided by which means flux, which is denoted as this, um, is equal to the charge inside it, right? Divided by epsilon naught. That's the overview of what? Gauss law. So now the question we have here is that what? Calculate the electric field due to a uniformly charged infinite wire. This is the uniformly charged infinite wire, right? So the charge per unit length is denoted as what? Lambda. So what we need to see here is that we can see that from this diagram, right, there is a uniformly charged infinite line, right, thin wire. It has charge, and we use a Gaussian surface, a closed surface, to cover what? The wire, right? So that the fields that will be radiating outward can be what? Enclosed in that what? Cylindrical Gaussian surface, right? So the surface has a length of L, right? So the electric field is E, and it has a radius of R. So the first thing we need to do is that in order to apply Gauss law to find the electric field, what we need to do here is that we know that since this is a Gaussian surface, right, the charge inside it, right, Q, or you call it small q, right, is equal to lambda L. Because as you can see, lambda, right, is the charge per unit length. So if lambda is the charge per unit length, that means lambda is charge per unit length, right? So therefore, since Q is equal to lambda L, right, and we know that from this diagram we have above, the electric field is radiating outwardly, because for a positive charge, right, it is radiating outwardly. So in that case, since we have like a cylindrical, like a thin wire, and the has charge, right, so it has to be radiating in this form. So if we enclose it with a cylinder, it will be radiating radially, right, through the what? The Gaussian surface. But the problem here is that the electric field will not be what? Coming out in this direction, right, and this direction. It only comes out what? In this side direction, but not the top and bottom direction, right? So in that case, let's apply Gaussian Gauss law, so we'll be able to know the electric field using Gauss law, right? So the thing we need to do here is that we just need to say from Gauss law, right? From Gauss law, right? The total electric flux, as we may mention, is equal to, right, the total electric field, right, over a area, right? This is a closed integral over a closed surface, right? Or you can write it like this: the electric field over a closed, right, surface, right? So the electric field coming out over a closed surface. So this is the electric field. This is the what? Closed surface, right? So by applying that, we will be able to solve for what? The electric field. So what we need to do here is that we say that since the flux, right, is said according to Gauss law is equal to Q over epsilon naught, so that has to be equal to the integral over the surface of the electric field over a closed surface, right? So we can proceed by saying that Q over epsilon naught, right, is equal to E, the integral over the AS, right? So this is the area of the surface, right? So the area of this surface is denoting what? Area of a cylinder, right? So the area of a cylinder is known to be equal to 2 pi RL. So all we need to do is to substitute it inside this, So we say that what Q over E naught epsilon naught equals the electric field times 2 pi RL. So then we can proceed by saying we know that Q, we can say Q, right, is equal to lambda L from the given that lambda is what the charge per length. So we can get what Q is. So Q now will replace it with lambda L over epsilon naught equals to E open bracket 2 pi RL. So we can end up cancelling this L, right? Because they cancel each other. Then we say E times 2 pi R equals to lambda over E naught. So we have to divide both sides by 2 pi R. So E equals, right, 1 over 2 pi R times lambda over E naught, right? So this is the electric field, right, of that thin wire, right, in respect to what? The lambda. So we are not just calculating the electric field as we used to do in other cases by saying the electric field is equal to K, which is a constant, then the charge over the R squared, right? No, we are expressing this electric field using Gauss law in terms of what? Lambda, which is what? The charge per unit length, and the epsilon naught, which is what? The medium, right? So why the other part is the area of the surface, right? So in essence, we can say that using Gauss law, whenever we are asked to calculate the electric field due to uniformly charged infinite thin wire, as the question denotes, right? Using Gauss law, the electric field is equal to 1 over 2 pi R, right? Times lambda over epsilon naught. That's the proving for it. So if you have a thin wire, just enclose it with a Gaussian surface. When you do that with a Gaussian surface, you can apply Gauss law, because Gauss law states that what the total electric flux out of any closed surface is equal to the total electric charge, right, which is inside it, divided by the epsilon naught. I hope the concept about this is clear. If you have any question, feel free to ask in the comment section and I'll be here to respond. Goodbye.